There are other ways to solve differential, higher order differential equations. We're going to look at what we call Laplace transforms. These are very, very useful when you're solving equations, differential equations that are initial value problems. They do need to be initial value problems, but they're also very useful when we have, let's say, a differential equation like mx double prime plus beta x prime plus kx equals f of t, or L, this is actually for a spring system, and then this one here, L, the second derivative I with respect to t plus R, the first derivative I with respect to t plus 1 over c I equals E of t. This is actually in circuits. So these are the two different equations that we see a lot of in what we work with. And the question is, how do we solve them as f of t and E of t are not constant? So what we mean by that is you can actually have a place where your driving force you would have in a spring system is not a consistent driving force. It turns on and off, or your electricity in your circuit, your power source turns on and off. So we want to look at how do we deal with those, and Laplace transforms actually solves that issue. Before we actually get into Laplace transform, I just want to remind you that the d of f of t is just another way of writing f prime of t. We use this notation a lot. This derivative notation is very useful in this day and age. We also need to define what a Laplace transform is before we actually look at how we solve equations with those. So we're just going to look at what the definition is. The Laplace transform is of a function f of t is equal to some giant f of s, we like to call it. And what we're doing is we're transforming the f of t into a new function. That's why the capital F. It's related to the small f, but it's a capital F, and it's going to have a new variable s instead of t. This uses integration to get to the new function with a new independent variable. F of t is defined on t being greater than or equal to 0. So we're never going to look at negative t's, but that's usually what we deal with. And the Laplace transform of a function is actually equal to the integral from 0 to infinity of e to the minus s of t, st, f of t dt. So this is what our definition of Laplace transform is. We are using an indefinite integral. So let's go ahead and find one. We're going to find the Laplace transform of 7t plus 3. And that again is the integral from 0 to infinity of e to the minus s of t, 7t plus 3 dt. So to find this, remember how we find these integrals that are not definite. They're definite integrals, but they're not, we call them indefinite, not indefinite, we call them improper integrals. We need to find out how we do that. When we're involving infinity, we will be looking at taking the limit as something, let's call it b, goes to infinity, of the integral from 0 to b of e to the minus st times 7t plus 3 dt. So we want to find this integral. Now you can just use any technique you want to find this integral. You can use tables of integrals, you can use technology to do it, whatever it does to find this integral. When I go to find it, I end up using technology. It tells me this is going to be 3s plus 7 over top of s squared minus 7b plus 3 s plus 7s, plus 7. And then this whole thing times e to the minus b times s, all over s squared. So when you find this integral, of course, you're evaluating from 0 to b, and this is what you would end up with. When I do this limit now, I need to find out what this limit is. 3s plus 7 over s squared does not involve b, so it could just, the limit of it is just itself, because it's just a constant in terms of this integral. In terms of this limit. This is more involved. The 7b plus 3 times s plus 7 all times e to the minus bs over s squared. This is more involved to find this limit. You can use L'Hopital's rule to find it because you're going to have infinity times 0. So you can use L'Hopital's rule to do it, but realize also, remember some things we learned from L'Hopital's rule is that e to a negative power takes over from a polynomial. So this is actually going to dominate in the end. This will all go to wherever e to the minus bs is going. And that happens to go to 0. So you get 0 over s squared, which of course is just 0. So that means this Laplace transform is 3 times s plus 7 over s squared. Now we're not actually going to find out what we're doing with it yet. We're just learning how to find these. So let's go ahead and do another one. Let's find the Laplace transform of t squared e to the minus 2t. That, of course, is the integral from 0 to infinity of e to the minus st times the t squared e to the minus 2t dt. So whatever's inside your braces here is what you're going to multiply e to the minus st times inside your integral. Again, you do want to make sure that you write this improper integral as the limit as b goes to infinity of the integral from 0 to b of e to the minus st t squared e to the minus 2t dt. Don't forget to do this step because you've got to do this integral and then take the limit. So now we're going to go ahead and do the integral. This is where you can use technology to do this. You can use tables of integrals. I don't care what you use to find this. When I go to do this, I would probably go ahead and e to the negative st and e to the negative 2t, right? That is e to the negative st minus 2t is one thing. But then it's just find that integral. And that integral happens to be 2 over s plus 2 cubed minus b squared s squared plus 2b times 2b plus 1 plus 2 times 2b squared plus b plus 1 all times e to the minus bs minus 2s all over s plus 2 to the third power. Again, this first term, 2 over s plus 2 cubed, does not involve a b, so the limit of a constant is just the constant itself. So it's 2 over s plus 2 cubed. The limit of the rest of this, again, you've got a polynomial on the top times e to a negative power in the top. That e to the negative power will go to 0 as b goes to infinity. This other part goes to infinity, so you have infinity times 0. Using L'Hopital's rule, you will find out that that is actually 0. So we now know that this is going to be equal to 2 over s plus 2 cubed. Don't always assume it's 0. I would check it out and make sure, but you can see it actually would go to 0. Let's try another one. Let's find the Laplace transform of f of t, where f of t is defined to be 0 when t is between 0 and pi halves, and it's equal to the cosine of t when t is greater than or equal to pi halves. Realize this is actually the power of Laplace transform. It allows us to actually do these transformations when we have this, when we solve a differential equation that has a function that does this, that it's equal to. Laplace transforms are very powerful for that. We're going to go ahead and do this Laplace transform of f of t. Again, that's the integral from 0 to infinity of e to the minus st times f of t dt. Okay. Now, this one's a little different because it's defined over two different places. Remember, you can actually take an integral and separate into different values by putting a constant in there. So we can actually go from 0 to, in this case, pi halves makes sense, but you can do anything you want, but makes sense to be pi halves. of e to the minus st times f of t, but from 0 to pi halves, f of t is 0. And you're going to add that to that, the integral from pi halves to infinity of e to the minus s of t, f of t again, but in this range, f of t is cosine of t, dt. So we just need to find this limit, this integral. Notice this first one's just 0, so we can actually not worry about this one because it's just going to be 0. The other one, it is an improper fraction, improper integral, so we do need to write it as the limit as b goes to infinity of the integral from pi halves to b e to the minus s of t cosine t dt. We haven't done the limit yet, so don't lose the limits. So now I'm going to go ahead and find that integral. Again, I would go ahead and use my computer or technology of some kind to do this. This is equal to the cosine of b times s minus the sine of b, all of that times e to the minus b times s, all over s squared plus 1, minus e to the minus pi times s over 2, all over s squared plus 1. This is the hardest part, is finding these integrals, and that's why some people don't like using this, but with technology, the integrals aren't too bad. Also, table of integrals, this is actually one of the table of integral would have this one as one of the values in the table. So either way works. Letting b go to infinity, again, you're going to have, not in this case a polynomial, you're going to have a sine and cosine function doing some things, but you still have e to a power, still can use L'Hopital's rule. You're still going to have 0 times infinity. I'm sorry, you're going to have infinity times 0 whenever you do this, or actually, in this case, you're not, because this is going to be the cosine of b. This is going to go between 1 and -1, so forth. A few other things, but it still is, this part's going to go away, and the e to the minus bs takes over as that goes to 0, it goes to infinity, that goes to 0, and the other part minus pi s over 2. So e to the minus pi s over 2 all over s squared plus 1 just goes to itself as b goes to infinity because it doesn't involve a b. And that means you're going to get minus e to the minus pi times s over 2 over s squared plus 1. Okay. Notice this is going to be kind of the same thing that keeps happening. We're going to keep going through these integrals, doing all this. And it turns out you can always will have kind of like tables of integrals. There's always going to be an answer that will always happen. Like the Laplace transform of 1 always will be 1 over s. You can do it. You can prove it to yourself. You can actually do the Laplace transform of 1 and show you will get 1 over s every single time. You can do the Laplace transform of t to some power. That will always be n factorial over s times n plus 1, where n is 1, 2, 3. It's actually positive integers. N factorial just means n times n minus 1 times n minus 2 all the way down to times 2 times 1. You can also see that the Laplace transform of e to the at is always going to give you 1 over s minus a. The Laplace transform of the sine of kt is equal to k over s squared plus k squared. Laplace transform of cosine of kt is s over s squared plus k squared. Notice the sine and the cosine are very similar, except the sine has a k up there, and the cosine has an s up there. The hyperbolic sine is actually k over s squared minus k squared. It's very similar to the sine one, except that the plus becomes a minus in the hyperbolic sine, in which case the hyperbolic cosine looks just like the cosine, except the plus becomes a minus in the hyperbolic cosine. Again, you can actually do these by doing these integrals and going from the definition. This is one that's very important, is the Laplace transform of a linear combination of f of t and g of t. So alpha times f of t plus beta times g of t. that is actually the alpha times the Laplace transform of f of t plus beta times the Laplace transform of g of t, which means we can do them in pieces. And so basically the thing of it is the Laplace transform of a linear combination is a linear combination of the Laplace transforms. There's a table that's in your book. There's tables on the internet. There's tables for Laplace transforms all over the place because it's kind of like a table of integrals. These will never change. They're always going to be these answers. So you can use this table to do these Laplace transforms. So let's go ahead and do one. Let's do the Laplace transform of 7t plus 3. So the first thing to notice on this is that I can actually have a linear combination of two functions. So let's actually do that as a 7 times the Laplace transform of t plus 3 times the Laplace transform of, well, 1, because you pulled the 3 out, it'd be 1. Now we go back to our table and we go and find the Laplace transform of t. Notice that's number 2 on this Laplace transform table, and that's 1 over s squared. The Laplace transform of 1 is 1 over s. So we know that this was going to be 7 over s squared plus 3 over s. And that's it. That's all there is to finding these. Notice we actually did that using the definition. So that was one of the examples we actually did a while ago. If I go back and look at that one, we did that here. The Laplace transform of 7t plus 3, we came up with 3s plus 7 over s squared. So you can actually see that that's the same answer we would get if you think about it. What we have is, if I try to combine these, I'd need an s here, so I have 3s over s squared, and then there'd be 7 plus 3s over s squared. So it all works out. Everything's fine. Here's another one. Let's find the Laplace transform of e to the t minus e to the minus t all squared. So the first thing I need to do is find out what that is squared. So that'll be e to the 2t. E to the t times e to the negative t is just 1. It's going to happen twice. So you're going to get 2 of them, so minus 2. And then you're going to have e to the minus t times e to the minus t, which is plus e to the minus 2t. So first thing I had to do was multiply that all out. Then this is the Laplace transform of a linear combination. So what that means, it's the linear combination of the Laplace transforms. So it's the Laplace of e to the 2t minus 2 times the Laplace of 1 plus the Laplace of e to the minus 2t. Going back to my table, the Laplace transform of e to the something t, in this case it's number 11, e to the alpha or at, is 1 over s minus a. So all we have to do is figure out what is what's a? A in this case is 2. So this would be 1 over s minus 2. 1 we already knew was 1 over s. So we have 2 times 1 over s. And e to the minus 2t would be 1 over s minus the a, which in this case would be s plus 2. And so there's your Laplace transform of that one. Let's do one more. Let's do the Laplace transform of the cosine of 5t plus the sine of 2t. Again, this is a linear combination, Laplace of a linear combination. That'd be the Laplace of the cosine of 5t plus the Laplace of the sine of 2t. Going to my table, the Laplace of a cosine is s over s squared plus k squared. So it'll be s over s squared plus k squared. K happens to be 5 in this case, so 5 squared is 25. Then we have the Laplace transform of the sine of 2t. Again, you don't need to memorize these. These are not things we memorize. We have tables. We looked them up. The sine of kt is number 7 in this case. That would be k over s squared plus k squared. So that would be k. K in this case is 2 because that's what's inside the sign. So it's 2 over s squared plus 4. And that's how we can transform these together. We will look later how we actually use this to solve, but this is just getting an idea of Laplace transforms.